You check?
Yeah. So, good morning, everybody. I hope you had a nice weekend. And let's continue with the fracture mechanics. And so to just give a short overview, what I was talking last week was basically this picture. So we have in our fracture mechanics, so this is basically the description of the stress intensity at this point. So at the crack tip, our three basic modes, which we are used to calculate with. So in this kind, the first mode always is the opening mode of the crack. So due to this, we also have at this part, at the crack tip, some stresses which are rectangular to the crack surface and are stressing our crack tip with the stresses mostly. So the second mode is a mode with shear forces on the surfaces, but also on the crack tip. So at this point, the shear mode is acting. And for the mode 3, we have here the distortion of our different crack models. And so due to this, also we get on the crack tip some shear, but the shear at the, if you would see the crack tip here as a bar, would act like the moment. So that's why you have here some distortion. And so the displacement for the third crack is a transverse to the crack direction, and that's why we say, okay, this is a non-planar shear stress. So, these are, just to get a little bit into again, these are our basic assumptions which are derived due to a coordinate system at the crack tip. And due to this, we also used here a cylindrical coordinate system. So as you can see here, you're calculating with R and theta. So that's why if you use here the coordinate system is always using the information due to the cylindrical coordinate system around the crack tip. So, and due to this, we just can analyze different mode shapes and also some basic information which we are later using, for example, in the testing assumptions. And also, for example, if you go and validate a numerical model, this would be also some basic analysis you always can do at this point. So, also what we started last week was like to go into with our first basic models. So this is, I would say, the basic models you have used or applied on different systems. For example, pipes, vessel pipes, also some agriculture factory machines, and so on. And for example, this is our first, the rurest and also the basic model, where we see, okay, we have here our plate, and the plate is going, and the crack is going through our plate. And so due to this, we just have here our K1 mode, and the K1 mode can be derived quite easily just by sigma times the square root P and A. And if you go, for example, to a more interesting models, for example, just on a surface crack. You just have also to do your analysis, but the analysis is already done by a lot of guys. And so you can use here, for example, these analytical models, which you see here for vertex. You can use K1, 1.05, 2 over P times sigma times the square root of PA, and also for the surface crack or for an edge crack. So this is basically the main models which I was introducing last week. And due to this, we started some analyzing of this sheet here, or this plate with the crack. And the crack was just going through our specimen. So also last week I got a question, okay, what is the difference between the fatigue design and the fracture design? And basically the fatigue design always starts with no crack. So there is like an ideal surface, you have no crack in your material, and this is basically the idea of the fatigue design. So it's just start with the information of the stresses, of the stress ranges, and also of the stress concentration. And this is mostly how you go and decide on your resistance curves, and at the end have to do your fatigue assessment. If you now go for some fracture mechanics, so this is, as it already said, you have to calculate with a crack. So this is the basic information you always have to start with. If you want to use some fracture mechanics or some fracture mechanic tools, you have to go and assume a crack, and also due to this assume a crack length and the size and the depth of the crack. So, for example, now we have here our linear elastic fracture mechanics. So this means that also next to the crack tip, there is not really a plastic deformation. So of course, the material always is a little bit ductile. So there are still some local plastic informations. But at this engineering model, we just say, okay, we just neglect this part because this part is not as important in our model, and so we can calculate here with linear elastic fracture mechanic. So what have we started with the model? So we have here our plate. The plate has some dimension, but at this level it is not important about the width of our specimen. So we just go and have here our information of the basic crack. The basic crack is here the 10 millimeters. We have a peak value for the stresses of 290 MPa and the lowest peak value of 0 MPa. So at the end also a stress range of 290 MPa. And also here we got some values due to our Paris law. So the Paris law is just the description of the continuous crack growth. So from this part, K over M. So this is our basic information due to the correct propagation. And so this value also have to be investigated due to testing. I will show later some movies where you just can see, okay, how is a crack growing, how are looking some specimens, and how is some some testing going forward. So for example, here, the C and the M, of course, they're investigated due to material testing. So at the end, the M also defines here the slope of our section 2, and the C defines the intersection of this curve with our y-axis. So if we're now going to go, for example, to this model, we see here, okay, we start just, in this case, I reduced the amount just to have a more smaller calculations in this sheet. And so at the end, you see here, this is just the definition of our section 2, so of the crab propagation. And at the end, just by using our formulas, you can calculate here the grid just by turning around the equation. So the grid would be here, the 6.4 millimeters. And due to this, you can also do some crab propagation, which has no information about changing loads. So it's in this case just a really simple assumption on the sinus. And also, as you can see here, how it looks like. So of course, with the increasing crack, our information of the stress intensity on the crack tip is growing. So due to this, also our curve is not linear. It is always something which is curved and which is at the end growing faster and faster. So this is basically what we have done last week and where we finished. So what I want to go today is some basic model which was applied during the 80s and so started in the 80s and now also implemented in some codes or in some guidelines. Sorry. To go into the presentation mode, is it here?
Yeah, because it's in Spanish.
Yeah.
It's in PDF, right? So
No, but okay. So, this is called the So this is called the fatigue assessment diagram, or FAD, and this basically goes back to the R6 concept, which was at first done by Mathias. And so this, of course, also is investigated due to some basic brittle fractures. So what we have seen also, or what I was talking last week. And due to this, the FAD diagram at the end gives you also some information. Okay. Gives you some information about if a system gonna fail under specific loading with a specific crack size. And due to this, for example, you can find this basically also in the FKM guideline. Or the BS 790101. And so this guideline is some British standard, which is just used, or which is done to get some informations due to the crack tip calculations and the crack calculations, but also due to the assessment of cracks and so on. So, and to start with, I just have here, of course, the J integral is something which is, for this I have to go a little bit a step back. So the J integral is something which is applied due to plastic deformations at our crack tip, but this is something which is also at the end introduced in the FA diagram, but what I do not go into today due to the time schedule. So more here also some basic informations on the testing method. So for example, the ASTM E1820 or E399 and 1290, giving here some guideline or some codes how to do some fracture toughness tests, but also how to evaluate at the end the testing. So how does it look like? For example, if you go now into the J integral, so the J integral at the end gives you some information between 2 and sorry. At the end, gives you some information about the potential energy, which is described by two identical structures with different cracks. So therefore, for example, you have here also the information on the crack size and also on the basic assumption. So what is the J integral at the end doing? We have here our crack tip, and due to our plasticity here, so we have here at the end what you're gonna also see in the videos is something that you have here, some plastic zone. And at the end, due to the plasticity, you cannot evaluate by just analytical information. So you have to go here with an integral, and this integral, which is just defined here by the circle, is also giving you the information about the deformation at the crack tip. And so at the end, you also can work here, for example, with the opening of the crack mouth. And so because you have here, at this time you say, okay, this here is completely stiff. Our surfaces are elastic and are completely stiff. And due to this, due to the information on the crack tip, we have here some information about the opening on our crack. And due to this, we can calculate here with this opening the J integral at this point. And due to this, we can calculate or evaluate our testing procedure and have here the information of our J integral, for example, just on the crack size, on the crack length, and also in this case is not really reliable on the structure itself. So yeah. So how does it look like? For example, if you see here, okay, if you go here, how does it look like next to our crack? So this is due to the size information in our continua, that we have a model which is always looking like a bone. And this bone, of course, has, due to the plane strain and plane stress information, in the middle of our section, less plasticity. And if you go to the surface, the plasticity is increasing. And this is just what is described poorly by this model. So complete. Okay. As you can see, there is something missing on the bottom, but it is not as important. No. So, so for example, due to this, we have done some testing on some historical steels, just to get some information on how is this information going to be reliable also for the steels today, because of course due to the production scheme and also to the better quality and we have now in our steel plants, the crystal structure is not the same, and so there are less defects in the material. And due to this, we have done in a master thesis some testing, and therefore, as you can see, some specimen, how they looked like. So at the end, just really small specimen of 100 millimeters to 24 millimeters and a width of 12 millimeters. And also here already you can see our crack inside our specimen, and also how the crack is defined, so just by 10 millimeters. So at the end, we have here 14 millimeters of material and 10 millimeters of a crack. So how does it look like? For example, so at first, we have here the PV curve, and so this is how it is tested. So we have here our force, so the graph in newtons, and at this side we have the deformation of our specimen due to a testing which so a 3-point test. And
yes, because let me see. Yeah.
Thanks. So we have here our PV curve, and so the test started at first with here some basic cyclic loading to have a correct initiation, which is not influenced or not really influenced by the fabrication of the correct tip here. So it first has to go there and approve some cycles. In this case, we just used 2 millimeters for the correct initiation, and afterwards the cycle loading was stopped, and it was just applied some force. And due to this part here, you can see how it looks like. Of course, it is still a 3-point test, and due to this, it is still looking like a tension stress-strain curve, so just like in a tension test. So, but due to this, of course, there are existing some guidelines or some material testing codes where you can see how you have to evaluate such specimens. So this is something which is here, for example, in the E1820, but also there exists some other guidelines, but usually you just use in this case the ASTM. So how does it look like? So you have at this point you have some initiation zone which can have some shifting just due to settling of the specimen, and at the next point you have to evaluate your linear curve. So this would be something like the modulus of elasticity in a tension test, and at the end you use this curve, take the 95% second, and at the end you get some information about your point PQ, and this point PQ has to be evaluated if there is some inclination. For example, as you have here, PQ, and also here, PQ. But for example, at this point, your PQ is before Pmax, and so this is also the point where at the end you have to evaluate. So for example, the Pmax is always the point where you have the most resistance. So, and at the end, your structure, if you're beyond this point, your structure or the correct gonna be fail. And so, of course, you have to define a point which is at the end beyond this point to have a conservative but also durable system. And so this is why you have, due to the different material behaviors, some different curves there. So how does it look like, a specimen like this? So for example, in the case of our historical steels, we had here specimen 3, 2, and 1. And of course, we always had our opening, but also at this side, but also on this side, our deformed state, and could at the end calculate or reassume our PQ, and also due to this analyze the J effective or the J plastic and J elastic, just due to our formulas. So how does it look like if, for example, if you go just about the CTOD is here the correct tip opening displacement. So this is what I meant before here. So you have here the correct tip, and this is at the end due to the just due to the displacement from the correct tip to the surface. You have the correct tip opening displacement, And at the end, you can measure the corrective opening displacement just by some small gauges which you apply onto your specimen. And due to this, you can measure and also the CTOD. And therefore, you also can calculate if you know about CTOD and also the delta A just by going there and observe with the microscale. You can get the information about the correcting opening displacement, but also about your delta A. So, and of course, how does it look like? So before we had here our curve of the different correct propagations. So here the DA and DN curve. And if we start our testing, we are also increasing our loads. And so we start here with an KTH, which is quite small. And at the end, we also get here some basic information about the KTA and our correct propagation. So, same results. So, if you now go and go in the ASTM 1820, you of course gonna analyze, as I said already, part 1 or section 1 and section 2 of the correct propagation. And so at this part, you have some, how to say, or start with this part. So you have some stable correct propagation, which is at this part just following the Paris law, and you can at this point analyze the slope of the correct propagation, but also the intersection on the y. So at this point, you can, due to the J integral, you can also define a law for the correct propagation in the section 2. But in this point, not regarding to the delta K, but regarding to the delta J. So, but for the elastic part, you also can recalculate from delta K to delta J. So, and on the same side, due to the plastic informations, you can also get some informations on the lowering part, which is here, or about the intersection. This is about the intersection, and the intersection at the same time is the point where we define for the correct propagation the KTH, and so this is also the point which is mostly interested here, to get the point where we have some stable correct propagation, and where we just have a starting information due to the correct size and due to the stress intensity. So this is, just go over. So, and at the end, we have here the information which are basically done for the elastic plastic fracture mechanics. So as we had last on Thursday, I was just talking about some information which was basically elastic. And on this side, we wanted to also go further and go into some small informations due to the plasticity next to our correct tip. And so at this time, we have some loading parameters, and the loading parameters are, for example, here, is just to have the word, I would say, the correct tip opening displacement, which is defined by the CTOD, or a value of rho. Then, so this is basically the information on the geometry, on the displacement of our crack. And with this information, we can recalculate our J integral, and also some stress release rate J, which is at the end, of course, our linear elastic behavior. So just to go, for example, if we go for example, to a tension test, which we at the end also give some cyclic loading. We have here some basic plastic information, but the plastic information is always in our material, in the system. And at the end, our material follows again our basic part of the modulus of elasticity. So at this part, we also can recalculate the elastic and the plastic behavior. And this is also something which is meant by the stress release rate. So this is something which is just due to loading. It can be the loading in the system, but also in the material testing. And due to this, at the end, we can define our material resistance, which is here the correct tip displacement opening, so the CTOD, and the JC, rho c, and also the J integral JC, which at the end, in just linear elastic behavior, would correlate with the KC or the KC1. And also due to this, we can also go into the crack growth definition. So in the Paris law, which we have here, dA dN, and here a function of J. Here we have just a function of delta K. And so due to this, also go and define our J sensitivity, delta J, which is at the end some definition, some function of a delta sigma, the epsilon, because we have to define or give some informations due to the induced strains, and also about the crack growth, the geometry, and the cyclic delta sigma curves. So this is something which is I have talked on Wednesday. So the cyclic J epsilon curves, this is where we go into, for example, a specimen and apply the incremental step test. So we have here some testing which is basically going like this, and inside this we have here our amplitudes, and due to this we can define the cyclic sigma epsilon curve. So this is the description of the material in a cyclic behavior, and so with this information at the end we can also recalculate the delta J. So of course, how does it look like for the safety check? Safety check, we have a J max, or this J max, which we calculated here due to our R value. At the end, has to be lower than the JC, and of course, also the rho has to be smaller than rho c. So, just description, parameters, and the units. So the K has a quite interesting unit. because it is here newtons over millimeters over 3.5. So that's why, for example, if you go there, for example, in literature, sometimes you have so just be not scared if there is some different definition of the units. They are always screwing up something a little bit, and also, as you can see here, also the MPa parameters are there. So this would be just again other defined than on the whiteboard. So how does it go? So we have now some basic informations about the description or about the models we have into the fracture mechanics. So as I said before, the fracture mechanics usually is just starting with the information of the crack, but also due to the loading, we have here different definitions about the F and also about the plasticity. So for example, for a small loading, we have here some linear elastic behavior, which is the EDC, means at the end plane strain behavior. So we have for a small loading, we have here plane strain behavior. If we get some more information into our material, we have this is what is meant before by the bone model. So we have some EDZ state in the middle and some ESZ, some elastic stress state on the surface. And then we get into ductility, so also our information about the load and deformation starts to get a curve, so to get an inclination. And at the end, due to, of course, more plasticity, at the end, our whole section is plastified, and we just have here the failing of the structure, as we have, for example, in a ductile model, but also as we would have, for example, in basically a tension test. So how is this part? For example, we So what have we to do if we go there and now want to go next to our FAD diagram? What do we have to know about the system, the structure? So at first, for our fracture mechanics, we have here the A0, and of course the K1C and the J1C. And also, of course, the description. Of the crack. So, but also on the second stage, if we now go to this part, we have to find a cross-section information where we basically can say for our bilinear stress strain curve without is it correct enhancement at this so without an inclination yeah, strengthening, thanks. Without strengthening. So we have here the ET is 0. We have to define also the model where we can say, okay, the F star is sigma times A star, and the A star in this part, for example, for a crack through model, is just the B times T times B minus 2 times A. And so we have to reorganize and see, okay, the C sigma star is F star over A star. And of course, this has to be lower than Fy. If it gets into really plasticity for a ductile material, this would work. Or if we have to carry on our K1C, this would be something which is going there, which at the end will give you the information about the assessment. So. So to start with, just on the first part, so about the fracture mechanics, I made here a summary of a thesis which we have done 2015. So there, the point of investigation was just a system of roller bearings, because I know is this kind of system known where it is applied? Yes, no? Yes? No. Okay, it doesn't matter. So for example, in old steel bridges, or usually in all bridges, you have a bearing support. And the bearing support can be some PTFE, some special construction. And so due to this, in Europe or in Germany, we use this kind of supporting of the bridges until 1960 and 1970. And then there have been some failures due to some material changes, and so of course the companies said, okay, yeah, we cannot use it anymore, and they investigated some new, some better supports. And so, for example, today you would use, for example, some callot, which is looking like this, or some rubber. And but before, this system was quite usual. And but also after 30 years and corrosion and a lot of use, this system does not work today, and so we have to rebuild it, enhance the systems, and also to build this kind of bearing situations again, just to do not redefine the bearing behavior and to give other forces into the structure. So, and due to this, there was started some small thesis to say, okay, which information do we have since then? What is some good estimations or some good constructive solutions to do this. And this was basically the start where this thesis started. So we had some old bridges, around 40 years old or also older, and we could calculate our stresses and also get some information about the KV. The KV is what I told you last week, the choppy notch impact test. So the choppy impact test, I found here a nice, which was short and also quite nice.
To show a type of mechanical test called the Sharpie impact test.
So,
The Sharpie impact tester has a
sorry.
and
So what he's basically showing here is some, so this is, for example, a really old basic Sharpie impact test machine, where we have here the hammer, and at the end the hammer is also defined, or the size and the weight of the hammer is defined by the material you're going to test. So basically what he's now doing is he's using this hammer, gives the hammer a potential energy, and is loading here or applying here the specimen. And then cut through the specimen, and this is basically what you're doing in a Sharpie test. So as you can see here, this is the specimen. In this case, it is quite ductile material, so it was a heat treatment material, as you said. And so also due to this, you have here this small deformation, and also on the side some flanks. Now he's going and using some other specimen, which is more brittle, so it's cold strength material. And due to this, of course, it has higher strength, or higher ultimate, or higher yield strength. And again, and as you can see here, the surface here, it is quite brittle broken. So you have, due to the higher strength in material, the material is more brittle. And you also can see it, for example, at this part, at the surface itself, but also compared to before, we had here information about our choppy energy of 28, and now it is 3.5. So a real reduction of the energy, and the energy, as we had last week, was defined by the potential energy we had in the starting point minus the point of return where the hammer goes back. And so as you can see here, due to this, the hammer was going really high. Due to this, we have here just a low fracture toughness in the choppy test, and or choppy test fracture toughness. And for example, for ductile material, which is of course can take more energy into the system, we have higher informations. So this was also done, for example, in this case, for different materials we got there. And so we could, go and investigate for different, or it was done to investigate different specific material parts in our bearing roller bearings, and also due to this at the end say, okay, to which material this could correlate to the definition according some standards. So in this case, it was used the older standard of the DIN 1681 and DIN 10293, and now we had to go into the system and get some basic information why these roller bearings could fail in the past, and what was the basically information on the material defect. So to go into, of course, what is the main definition or the main description of the stress state there is of course done by the Hertz pressure. So we have here some contact information, and due to the loading at this point we have the highest pressure, which are also going above, theoretically above the yielding point, but due to the three-dimensional state, usually you're always under the yielding point, and you can describe here the information in the y direction by this quite easy formula. So due to the misalignments in the roller bearing, we also said, okay, we have 4 bearings, but just 3 are carrying loads, and the other one is free. So how did it look like, the failures in the 60s? The failures were just splitting up our roller bearing. So at the end you had 2 pieces. If you want to have some load carrying movements also there, you can see, okay, this would not be able. So at the end, there has done some numerical investigations. So as you can see here, again, the 4 bearings, because just to go here, this was a quite analytical way, just to go there and get the information roughly, and at the end could estimate some information on the 3D model. So that was also done with just the 3 bearing conditions. And at the end, of course, the convergence from the analytical to the numerical model, so it worked quite well. And how does it look like if we now go into our stress state? So next to our crack tip, of course, we have here at this part the high pressure. Next to, we get into some tension zone, and here, as you see here in the half moon, this is how the stress is acting on the roller bearing itself. So, but still, why is our why do we have some cracks next to our roller bearing? So we said always the cracks just appear due to tension information. So, but as you can estimate here, we are loading the bearing, so we would assume at first just some information which are basically our pressure on the surface, but also on the bearing itself. But due to the 3-dimensional stress state and the Poisson ratio, you can see here that, for example, this is the part where you have the contact zone, and next to the contact zone you get some information which is just on tension, and due to this tension information, of course, this is acting, for example, also on our crack tip. But also At this part, there is some shear stress, which are also acting directly at the end of the roller bearing onto cracks next to the ending. So this is some specific view. So you can see here, this is the ending of our roller bearing, and here we have our direction. There's still some tension and pressure inside. So which model is going to be applied? We have here, as we said before, we have here the stresses which are going into this direction. So we always said before that the most important case for crack growing at the end will be the K1 mode. And so we also applied a crack model, which is at this side just going into the direction of the main stresses, of the main tension stresses. So how is it looking on our model itself? So we have here the tension, which are going longitudinal of the roller bearing. And at the same part, we have to apply here some crack model. So this is some surface crack, which is applied, just described by 2C and A. And also, due to literature, you can find often some information which gives you some basic information about the crack, of the crack size, which is due to manufacturing. So, for example, for the drilling, or also some other improvements on the material, you can find here some formulas, for example, for the A here of 0.5 ln T over T0. So at the end, this is the basic information. So you have a T0, this is the reference, and the T at the end is the value you apply to, or which you want to investigate the blade size. And so you have to apply here some crack, and due to this, you see, okay, you have here some crack depth. So this is the A, and the crack width is the 2C, and the 2C are just easily calculated by the two formulas, or you can take it out of the diagram. So at the end, due to the surface model, you see here just the basic calculations. This is some formulas you can find in the FKM, you can find in some guidelines of the IAW. And due to this, you just get, due to the description of the crack size, due to the applied stresses at the end, you get in the linear elastic behavior the K1. So this is the K1 mode. And you can see here, it's just the 2.9 Newton millimeters over square. And also, if you think about the model itself, we used it first description of the crack model, which was going like this on our roller bearing system. So if you now look on the failing situation, so this is our error, how it looked like. The error does not really describe how the roller bearing failed. So for a model like this, or for a crack like this, you would assume that the crack is going here, and at the end, it is just divided into two pieces. And this is also some failure which appeared, but not as often. Or something which would go like this. So at the end, it is just going with the 45, 30 degree, just on the failing situation. So again, going to literature, and at the end, we could also find some basic analytical model which could describe a crack inside of the roller bearing situation, which was just defined due to the tangent, due to the diameter, and using this model again, you can see here for the same situation, and using the stresses, you have acting due to the tangential loading. You get here a K1 mode of 5.03 and a KT mode of 32.53. And so you can see in the assessment itself that, for example, for the basically model we had there, we just got in K1 of 2.94 for the first model, so which was applied at the ending of our roller bearing. If we applied a crack model which was related to the arrow itself, we got at the end a K2 mode, which is here the 32.53. And due to this, you can also see, okay, for the crack propagation itself, it will end up in the K1 mode. But for the failing situation, which we had here, you also have to think about the K2 mode, because this was at the end the mode which was reliable, or not reliable, which was necessary, and also the most important for the assessment itself. So, how was the K1C defined at the end? The K1C is defined by this formula above, and this is just a rough estimation of the fracture toughness. And this fracture toughness at the end is defined due to some Charpy tests. And so in this case, it was also possible due to the materials. So for some materials, there has been some enhancements to define some empirical models for the K-MUT. And this is the KC. To at the end have the information to go there, and just with the Charpy test, which is much more easier, give some first information on how the model or how our situation will fail and how it's going to end up. So, the example of the roller bearing was just a short example on how you can, for example, work with fracture mechanics and also define, of course, the failing mode, but also to describe the failing mode, but also to give you the first idea what informations do you need to give the first ideas. What I forgot here. As you can see here, of course, our proof of the assessment of the roller bearing was in this model. It was good because it is just improvement of the material at the end which was used. And for example, if we applied here also some older material, there we just had for this model here a K-mat or K1C of 15, and this was also at the end the roller bearing which failed. So which failed like this. So for example, here you can also see for the older material which had the really problem, we also got the right description due to the fracture mechanics, but here it is just done for the new material. So the fatigue assessment diagram. So the fatigue assessment diagram is now something which is going again into the design, but at the same level wants to go there and also take care about some elastic informations. But just used or just applied due to the information of the linear elastic fracture mechanics. So here about the K values. So how is our axis defined? So at the y-axis we have here the KR, and the KR at this situation gives an information about basically the fracture toughness, so the K1C. So this is also the failing situation, and also at the same time about the K1, which is our loading situation. And the y-axis at the same level gives you just the loading information, basically the loading situation on our system. So we have here the sigma, so our loading. So are we still in a low level of the elastic behavior, or are we going next to yielding situation? And due to this information, we can combine this by a limiting curve. And due to this is basically what is done in the FID diagram, so that you combine the information of the linear elastic fracture mechanics and some yielding information, which is just roughly done by typically engineering calculations. And so at the end, the limiting curve is described. So, and of course, the investigation of the loading is done just by uncorrect model. So, for example, in the case of the roller bearing, we also were just calculating the idealized roller bearing, and at the end, due to the stress investigation, just the correct model was applied. So for this, we have to do some first steps. Of course, we have to use the loading situation and also the correct size and the material properties, and for this define the distance to the critical conditions. the next stage or next information. We get the information about the critical loading and also about the critical fracture toughness. So at the end, for example, just due to the information about the stress state, we know about the yielding point. So what are the information basically our material has to handle in a static analysis, but also basically due to the crack assumption, due to the loadings, you get the information, okay, it has the material itself, the right fracture toughness, so the right information about what is going on next to the crack tip. And so at the end, here it is combined. So how does it look like? We have here our FID diagram, and the FID diagram, of course, has here at this part the brittle failure. So this is the part where we have a K1 similar to K1C or above K1C. But as you can see, okay, if you're still if the KR, which is defined for K1 over K1C, is beyond lower than 1, you're on the safe side. If you're above the curve, you're on the unsafe side. So it is, I would say, quite easy to go into the diagram. And on the other side, you have here the information about the static analysis, so about the stress state in your material and also about the yielding. And of course, if you go, for example, more onto this side, you're next to your yielding point. And of course, you have here also some information about the elastic plastic behavior next to your crack tip due to the stress increasement. And so due to this, you have here some lowering of your behavior. So how does it look like on a so this is, I would say, this is here. This is just the basic information which was done by the RS6 concept. And this is, for example, just for, as it is always called there, for the option 1, which has, of course, here less plasticity. If you, for example, go for the R6 concept option 2, you also get here some further information about the plasticity, about some information about due to the plastic collapse, where you also take account about some strengthening of your material. So, and where you go also above the Fy, so above the yielding point. So the yielding point, of course, would be always here at this level. So this is described by the R6 option 2. And so, for example, if you're here, for example, for the green point, this is something you go out to some inspection of your structure, of your bearing system. You find a crack there. You know about the behavior itself, you know about the crack size, and then you can see, okay, still you're here in the zone which is still acceptable. And then you know, okay, nope, it's gone. you have here the dAdn over delta K. And so you have your basic information about your material because you were able to conduct some correct propagations, or you can, and so you know, okay, for this point here, there are still some time left where your crack can grow, and this crack growth is always, or is in this case, described by the crack propagation. So due to the crack propagation, this point is moving from this point upwards and gets here critical. And then of course, if it's going above the line, you're in the uncritical side. So at the end, your system, your crack, gonna fail. And this is basically described here by the FID diagram. And of course, due on the next step, this is also what is done until here. So also for this step, you have to go there and also do some basic analysis just on, is it really proved that the cross section can still handle the correct amount and the correct size? And this is basically what is described here. So how does it look like? For example, if you go for some investigations on the material. So you have here, this was a project which was done by a colleague. So at first, there were done a lot of tension tests. Sorry, tension tests. So you have here the stress and here the strain. There for different part of a railway cross section, and due to the informations of our tension test, she was already able to draw the FID diagram just by what is going on in the material, just by describing mostly this part here. But of course, for the fracture mechanics, so for the definition of the crack of the K1Z, she also had to conduct some fracture mechanics testing to describe at the next level the K1Z and the J1Z. So, but just by using the information of the tension test, it was already possible just to go into the diagram and to get the basic information on where is some information due to some yielding and where is some enhancement, for example, next to the plastic collapse. So again, what are here the basically assumptions? So if you go into the diagram, you see here the LR, which is here 0. So this is the yielding point, which is related to a curve which has no strengthening in the material. But for example, if you go above, if you want also go into the yielding point, you have here the area which is above 0.1. So then also there are two options, option 1 and option 2. Option 1 is basically has less yielding information. So there the difference between the yielding point and the ultimate stress strain is less. And for example, if you go for a material which has more informations, then you can also go to option 2. So this is basically the description of the formulas. So which were conducted due to the R6 method. And yeah. So, and again, some small example. So this is basically the informations what you have to get if you want to use or to go into the fatigue assessment diagram. So of course here I just have the modulus of elasticity to describe the model, also the Poisson ratio. Then in this case the width for the crack through model. And here basically the information out of our tension test. This is the surface temperature, so I set here 20 degrees. And in this case, I also used the estimation of the fracture toughness due to the Sharpie test. And also on this time, you have to know about the temperature for the 27 joule information of the Sharpie test. So this is, for example, if you go here, we have here the information of our Sharpie test. So we have here the brittle fracture for low temperature, and for high temperature we have the ductile behavior. And from this port to this port there is the elastic plastic behavior, and the T27 joule in this port is just describing where we have the 27 joule and the related temperature. This is something which is defined due to the material which we want to use in Europe, and so this is something which is on this level related to this. And so, for example, you can go there and do the calculations of the K-mat due to some fracture toughness test, which I'm going to show at the ending. And the other one would be for some specific materials, so for some meal steel, which are widely used. You can also go there with the information of the Sharpie test and analyze there the K-mat and also get you the basic informations. And now you can go and just draw due to the informations of the tension test. Here again, the FID diagram, and at the end analyze the model and define, okay, what point is here. If you're here for the assumed crack length, you can also calculate the critical crack length and give you the information back about the stress state there and the loading situation there. Okay. So this is a quite old movie, but which is also done by Instron. So Instron is here the supplier of the testing machines, and he has here the specimen. He's applying there the clip-on gauge, which is just measuring the opening of the specimen, and due to this he can recalculate the information on the crack tip. So as you can see here, at first Yeah, I think it already starts. You can see here some small movement in the specimen, and this is just the information due to the cyclic loading. Then the crack is defined, and afterwards they start just go through like in the 3-point bending test. Then you can see here the crack tip ends, and you get the information about the plastic deformation on the crack tip, and the crack mouth is still opening. And here again, the load displacement curve. So as you can see here, at first you have a quite elastic behavior, and then at the crack tip it starts to plastify, or the plastification starts, and so you also get the curve, which at the end looks like in the tension test. Okay, so this was the first session for today about the crack, the fatigue assessment diagram, so which is mostly applied to structures to assume or to get information back about the crack size, about the loading, about the maximum crack length, and also about some plasticity which could be applied onto your model. But also here you have to be sure on the material behavior, after the yielding point, and also about the microstructure. And in the second time, I just want to go into again into the evaluation of some fatigue tests. What is here the basic assumptions, and what are the basic methods which are applied there. Okay, so I would say let's say in 15 minutes and start again.